We are finally ready to look at the final project for this course. So 20% of your grade will be a design of an 8-bit microcomputer. So you are actually going to design, simulate, and implement an entire computer system in VHDL. And this is going to hopefully bring together everything that we have covered in this class, everything ranging from combinational logic design, sequential logic design, RTL, memory systems, finite state machines, and registers. So the computer system is quite large, and so one of the things that we do is break it down into deliverables so that you make sure that you get a certain portion of it working before you go to the next step. If you wait until you get all the way to the end before you start debugging it, then it becomes very difficult to debug. So we do this just the way that you would design any large digital system. We break it into multiple parts that you will deliver as you go. Just for reference, there's 4 parts that you're going to have as a grade. Part 1 is going to be called a VHDL shell. So you're going to complete 2 very small multiple choice quizzes on computer hardware and software, and then you're going to build this VHDL shell, which represents all of the inputs and outputs of all the files that are in your system. In this situation, you're actually going to have 8 different VHDL files. And what you're going to do is you're going to build all these files, create them, get them named accordingly, set up all the entities, and then add in any component declarations and instantiations of any lower level files. What this will do is part 1 will allow you to actually simulate and test that the connections all the way from the top level test bench all the way down to the lowest level component are accurate. And that is a significant accomplishment because there's so many ports in this system and so many lower level components. You want to make sure that all the inputs and the outputs are wired correctly before you add any functionality. That'll be worth 10% of the overall grade. Then what you're going to do is you're going to design 4 basic instructions in the computer, and you're going to perform a model simulation. So this will allow you to essentially get the entire computer system working. You don't need to implement every instruction in the instruction set to make sure that the hardware is working. What you can do though is you can get the memory system, the data path, all of the input and output register logic in there, and then you can design the finite state machine within the control unit to perform the fetch, decode, execute on just a subset of instructions. So you're going to do these 4 basic instructions, which are load register A with immediate addressing, load register A with direct addressing, store register A with direct addressing, and branch always. This will allow you to essentially get the vast majority of the computer system working, and you will perform model simulations to verify that. Now 40% of the grade is the largest chunk of this project is this part, because this is where you're actually adding all the functionality to do everything. Part 3 is you're going to take your computer and you're going to implement it on the FPGA. So you will actually take the computer system and drop it into a top.vhd, and you'll wire all the ports of the computer to the basic I/O on the FPGA board. And this will allow you to actually put a program on your computer and write and then run it, and you'll be able to read in information from the I/O on the FPGA board, so things like the switches. You'll be able to do things like store them to LEDs or the character displays. You'll be able to do things like addition and test that all of that is working. You'll be able to just monitor whether the computer is running in real time in real hardware. And then that's where 20% of the grade. So you'll essentially get to the point where you've built up 70% of your grade. And then part 4 is if you would like to continue adding more points to your overall score, you can essentially just implement more instructions. So implementing more instructions will give you essentially 2% for each instruction that you implement. And all you're going to do in this is just every instruction that you want to implement. I give you a list of the ones that you can do right here. You go in, add the logic to the control unit, and then you make sure that the logic is supported within the data path, and then you run a simulation, and then you implement it on the FPGA. To do this, you also have to implement design the state diagram, but then each one of these that you implement can be worth 2%, and if you do all 15 extra instructions, you can actually get to 100% on your project. Let's take a really quick look at the overview of the computer. So let me start with just the computer itself, and then we'll talk about the FPGA implementation. So when I look at this computer, what you'll see here is you're going to implement this in a computer.vhd, and within it, if the first thing you look at is the ports. Okay, so if you look at what comes into this computer, you'll notice that you have 16 input ports and 16 output ports, and then you have a clock and a reset. That's all that goes into the computer. A computer interfaces with the outside world using ports. Okay, so then how do you tell the computer what to do with that information? Well, that is the program. That is what you will do, what you will put in your program memory within the memory system. Inside of the computer, you're going to have two main components. One is going to be a CPU, central processing unit, and one's going to be a memory system. Within the memory system, you'll have your program memory, your data memory, and your output and input ports. And then you need a bus system to communicate between the CPU and the memory. In the CPU is going to be your control unit, which is the big finite state machine that knows how to execute all the instructions. And you're going to have a data path, which is going to contain all of the registers and the ALU that will actually hold information and manipulate information, and also produce things like the address to the memory system, and also keep track of where you're executing code in the program memory. Between these, you're going to have an address bus, data buses, and then a control signal, which is just simply write. The way that we break this down is we only have unidirectional buses in our system, since this is on chip, and so we'll have one bus that goes from the CPU to the memory, and another bus system that comes from the memory back to the CPU. So that's the overview of the computer level. Okay? If you go down one level and look at the CPU, you're going to break that down into the control unit and the data path. The control unit is literally the finite state machine that runs the entire computer. It is a finite state machine, so it looks at various things that are going on in the computer, and it produces outputs. It is in charge of doing the fetch, execute, or fetch, decode, and execute operations for each instruction. To do this, it's going to have a lot of signals that will tell the data path what to do. A lot of times it's telling registers to go ahead and load information that is present. It's telling multiplexers to route information from one register to another. It knows when information comes in from the memory system and when it can be loaded. It also knows when to increment the program counter to keep track of where you are in data memory. It also knows what operation should be being conducted in the ALU, so it can tell the ALU what to do. So this is the control unit, and it's going to be this big finite state machine that sits within the CPU. The data path is where the RTL logic is. So you're going to have all the registers that you need in your computer. You're going to have multiplexers, which facilitate signal routing. You're going to have the ALU, and this is where information from memory comes in and where information to memory goes out. So that's going to be the CPU. If you look at the memory system, there's two important components of the memory system. The first is the block diagram, which you see right here. So you're going to see this memory.vhd, and then within it you're going to have program memory in the form of a ROM, you're going to have data memory in the form of read-write, and you're going to have output ports, which are in the form of 16 independent registers, each with an associated address. And then you're going to have the input port logic. And the input port logic is actually nothing more than just routing specific input ports to the output of the memory system based on the incoming address. So the input ports don't get latched. But this is what the memory system is going to look like. The way you implement it is the program memory is implemented as a component. So it's going to be called ROM underscore 128x8 sync. And then you're going to implement the data memory using a read-write memory. Then again, the output ports are 16 processes, which can sit at the same level as the two component instantiations within the memory. When you implement this, what's important is that the memory map has already been created for you. So what I would like you to do is you have 8 bits of address. That means you can address 256 unique locations in memory. So what we're going to do is we're going to use the first 128 bytes, the first 128 locations in memory, to serve as your program memory. So this means that address 0 to decimal 127 or address 0 to 7F hex represent the information that's in this ROM right here. So you have to hard code within this ROM to those addresses. Within the data memory, you're going to have 96 bytes of read-write memory. So you're going to go from 128 to 223 decimal in terms of address, or you're going to go from hex 80 to DF. And those addresses are going to be hard-coded within this read-write memory system. Okay? You are going to have 16 output ports, which are mapped to specific addresses, E0 to EF, and those addresses are reflected in the implementation of the 16 output port processes. You are also going to have 16 input ports, which are mapped to F0 to FF. That means whenever you see those addresses between F0 and FF, you will then route that specific input port through a multiplexer in the memory system, and that will be the output of the memory system itself. Okay, so those are the main components of the computer, and you will implement these as you go. And it seems overwhelming at first, but as you start working away at it, you'll see that it's doable. Let's take a look though at what you do with the computer after it is operational. We can actually take it and we can put it within a top.vhd and implement it on the FPGA. Now we do this to make sure that it actually works in the real world, but if you think about a computer, the only inputs and outputs are through ports. So you see this computer, you have 16 input ports, 16 output ports, and you have clock and reset. What we do is we don't touch the computer once it's in here. The only thing we would change is the program it's running. So we need some input ports. So what we do is we map the 8 switches to port in 00, and then we take the 4 keys that are on the FPGA board and map it to 01. We go ahead and just bring in zeros for the upper 4 bits because we only have 4 keys. And then notice that all these input ports here are just dangling. We don't have any other inputs that we need to connect to them, but that's fine. We'll just leave them. On the outputs, we'll go ahead and route port out 00 to the red LEDs. And then what we'll do is to view the contents of port out 01, 02, 03, what we'll do is we'll connect them to 2 card decoders. So remember, your card decoder takes in 4 bits, and so you'll be able to see, you'll use 2 card decoders to look at the 8 bits of any one of these ports. So when you, let's say you stored the port out 01, you'll see the hex value on hex 0 and hex 1. And then similarly, port out 02 will be on hex 2 and hex 3, and then port out 03 will be on hex 4 and hex 5. Since we do have additional output availability, we can put 04 out to GPIO, the header, pins 7 to 0, and then we'll go ahead and put port 05 to 15 to 8. So that's how you wire it up on the FPGA. And what you want to do is you want to run it, but we'd like to be able to just slow it down so we can see that it's actually performing what we expect. So as a result, what we want to do is put the precision clock divider in here. So we're going to have the same reset that comes from the reset key on the FPGA board. We'll have our precision clock divider that we've done before. We'll bring in the 50 megahertz clock, and then what we'll do is we'll use 2 switches to select a frequency. We want to go ahead and move the switches that control the clock frequency up to switch 9 and 8 so that we can have the inputs switch 7 to 0 show up directly on LED R7 and 0 if we wanted to test that we could read from port in 00 and store to port out 00. Okay, so that's what the FPGA implementation looks like. And so then finally, I give you a lot of the functionality that you will be implementing. The first thing is when you look at these block diagrams, you're going to be implementing these pretty directly. Okay, so you're just going to look at something like the data path and just talk about, well, the instruction register is a register. What do I do? You know, when I see a clock and when I see a rising edge of a clock, if IR load is asserted, I'll grab what we call bus 2. So you can implement a lot of these based upon the block diagrams. When it comes to the control unit finite state machine, you need to know what the logic is. So what I do is I give you the state diagram for the 4 basic instructions. So for load A immediate, I give you exactly what you should be implementing. You should be able to code this in VHDL using the 3-process model for finite state machines pretty easily, because you're just going to code this stuff up and plop it right down into the control unit, and then you'll test it by putting a program in your program memory and making sure that it executes. When you implement these, you will simulate them, and I show you exactly what the simulation should look like. So you're going to have you're going to observe your current state, and you should see the state transitions directly through the path that you expect. So fetch 0, fetch 1, fetch 2, decode 3, load a immediate 4, 5, 6, and then start over again. And so you should be able to produce these exact waveforms in ModelSim that I give you in the handout. Okay? All right, so in the next set of videos, what I'll do is I'll give you more details about the specific parts of this project, but hopefully when you get done with this, everything that we've covered in this class will be brought together into one single large-scale digital system design.